Welcome back. This is about parallel impedance loads and impedance simplification. So you're given this little funny notation here just to throw you off. There's a voltage source that's a 60 hertz source and it has this plus minus polarity. Does it matter in this problem? No, but they're throwing it on there. So domestic power in North and South America is 60 hertz. In much of Europe, it's 50 hertz. And I learned recently that in Japan, I think half is 50 and half is 60. Like the north is 50 and the south is 60, something like that, I think. Or maybe it was voltage that's different. Anyway, that happens to be true. It doesn't really matter here in the way that the problem's set up. But anyway, they've given you these three impedance loads in parallel, right? Which is the way these guys are hooked up. So typically, so there's these three loads and they're hooked up in parallel to this voltage source. So that's what, that's typical. You in your house, you'd have a 60 hertz voltage source, and then this could be your toaster, and this could be your computer, and this could be your anti-asteroid laser, if you happen to have one of those. I like to be prepared. So what we're asked to find is the power factor and the reactive factor for each load. And we're asked to find the power factor and the reactive factor for Z equivalent. So individually, what's the power factor on this guy, and this guy? And then what's the equivalent impedance seen by the source? And what is the power factor and the reactive factor of that equivalent impedance? Okay, so part A. So it's a pretty easy problem. It's kind of a little, I squished a bug there. Springtime, these little bugs come out. So load 1, impedance 1 is 240 plus J70. So in polar form, by punching your calculator, you get this thing, 16.26 degrees ohms. So you can draw the little triangle. So this is going to be 16.26 degrees in here. This is going to be 250. This is going to, down here, this is going to be 240. And this is going to be 70. It's a 7. Okay, that's the little triangle. So the power factor it's just cosine of the angle, 16.26. It's 0.96. And we say this is lagging, okay, because it's an inductor. We know it's an inductor because the reactive component is positive, right? So Z sub L is or X. I guess X is greater than 0 and theta is greater than 0. The angle's positive. The Q component goes up, and this is Eli. And the reactive factor is sine of 16.26. It's 0.28. So you have to use lagging or leading terminology on the power factor, because once you've calculated the 0.96, you've lost the sine of the angle in here. So you have to capture that by saying that it's lagging. That's what the term lagging and leading is. It's to capture whether the angle is positive or negative. That's it. So Z, same thing 3 more times. So Z2 is 160 minus J120. In polar form, it's going to be 200 angle minus 36.87. If you drew the triangle, it would go down like that. So the X component is less than 0 and theta is less than 0. Theta is negative. So the power factor is cosine of negative 36. It's 0.80, and you have to say leading to capture the fact that the angle is negative. It's capacitive. Both these two are capacitive. This one's inductive. So you can say it's ICE. And the reactive factor is the sine of minus 36 degrees. It's minus 0.60, and the sine is captured, so we don't have to say anything else. Okay, Z2, pretty easy. Prop 3 minus J40, and the polar equivalent is 50 minus 53.13 ohms. So the power factor is cosine minus 53. It's 0.6, and you have to say that it's leading, or it's ICE, which once again the angle is negative, and the reactive factor is sine of minus 53. It's minus 0.8. Okay, so the equivalent. So that was part A, and the equivalent is part B. So these guys are three separate impedance loads in parallel with each other. So we can use our parallel simplification. Too many R's in there. Parallel simplification. So Z equivalent is just 1 over the reciprocals of these three things, right? So it's 240 plus J70 on this guy, and 160 minus J120 on this guy, and 30 minus J40. So take these three reciprocals. You need a calculator, right? You don't want to be doing these by hand. All those J's, you're going to mess up a sign for sure if you do that. Try and do that by hand. So even getting them in your calculator right is kind of a challenge. Anyway, calculator will tell you the answer to this thing is 27.81 minus J25. It ends up being 37, angle minus 42 degrees. And the power factor is cosine minus 42. It's 0.74. You have to say leading to capture the fact that the angle was negative originally, and it's overall ice. And the reactive factor is sine of minus 42. It's minus 0.67. So overall, the equivalent circuit happens to be ice. Let's see. So we didn't need this fact that this was 60 hertz because we were given these J values already. If you were asked for time domain, right, then, right, if you were asked to go back to time domain, you would need to get omega out of this, right? You'd need to get omega in radians per second, right? Convert 60 hertz to radians per second. And you could take apart these J's, and if you were asked to get the capacitance and the inductance in, farads and henries, that's how you do that. Okay, just a little playing around with phasors.